Okay, good morning, everyone. And today we will continue our lecture from yesterday. Um, we considered optical properties and electrical properties are also important in the sense if you want to build electrical memory, you need to know some basics. So just let us consider one basic of each material. This is a band diagram. Uh, from previous lecture, we already know that the band gap of amorphous and crystalline phase change materials, they are they differ between. So we considered optical band gap. For amorphous, it was like 0.5. Here it's 0.7. So there are some reports on the band diagram, and it's found that if you consider amorphous GST, this is AGST, we have here conduction band and valence band. We know that in amorphous materials there are Urbach tails close to the valence band and conduction band, and some measurement shows that the Fermi level it's located close to the valence band in the amorphous material GST or phase change materials. So in the crystalline, there are no Urbach tails, and the Fermi level it also close to the valence band, but it's located a little bit more deeper compared to the amorphous phase. If you look here, so it's more deeper. Uh, so what we conclude from here, we can conclude that based on the Fermi level that it's close to the valence band, both materials, these are p-type semiconductors. Here it's also in amorphous GST, it was found that structural defects along tellurium chains, they give a high density of donor and acceptor like traps, so you can dope this material. And presence of structural vacancies, we will consider later today about the structure. In crystalline GST, it leads to the acceptor-like traps. This is because of vacancies. So now, also one important property of materials, it's also electron transport. And we consider the electron transport mechanism and phase change materials. But before to show some results, I would like to show you like a short introduction to the electron transport, how to classify the materials by temperature coefficient of resistance. So this TCR, this coefficient can separate between metallic and non-metallic behavior of your materials. So you measure how to proceed. You measure the resistance and independence on the temperature, and then you look to the change in the resistivity per each degree. And then if you find that the slope of your material is negative, then it shows non-metallic behavior. If the slope of resistivity it's positive, like it shows this behavior, then the material is metals. So metals show resistivity increase, the increase in temperature, and non-metals show thermally activated charge carrier transport. Now let us look to the phase change materials, how they behave. So there are several reports on the transport mechanism in phase change materials, but this is one paper which based on the epitaxial thin films. So they produced different states of materials, starting from the amorphous state, and then cubic phase, and this is vacancy ordered phase and trigonal phase. So the three crystalline phase, they differs in the structure, in the sense of on ordering of vacancies. So here the cubic phase, it has vacancies which are disordered on cation sublattices, and here they have vacancies which are ordered on specific planes today we will also consider this. So, and what was found here that this is the resistivity against the temperature measured from 0 Kelvin up to room temperature. And what we can see that the amorphous material and the cubic phase, these are both relevant for phase change material, for the phase change memory. This they showed like non-metallic behavior. So here this is the slope negative. Here you see this is negative. Here it's also a little bit negative. So they showed non-metallic behavior. And the other two crystalline phases, like vacancy ordered and trigonal phase, they showed a positive slope. So they are metallic conductor. And so this transition between non-metallic behavior to metallic behavior, it's driven by the ordering of structural defects in the structure, and in particular, this is the vacancies which present in this phase. So now let us look to another effect. There is also so-called metal insulator transition in this system. And let me also first to define what is it and how to measure it. So IOF regular criterion predicts the existence of a metal insulator transition. Then this term KF AE satisfies the criterion KF proportional to 1. So KF, this is the Fermi wave number, and LE or lambda E is the elastic mean free path of the carriers. And according to this IR criteria, if this KFAE large, then larger than 1, then this is metallic. And if it's lower than 1, this is insulator, so it shows insulating behavior. There are two types of such metal insulator transition. One is driven by Mott, and another is driven by Anderson. In the case of Mott MIT, you have a metal, and if you decrease the doping in this metal, you can go from the metal to the isolator. In the case of Anderson MIT, here this effect, this transition, is driven by increasing of the disorder in the material. So if you start with metallic behavior, it's not with metal, and then if they can increase the disorder, we can go from metal to insulator. So in the case of phase change materials, it can be also measured. It was published in this publication. And the author found that if you increase the temperature in the crystalline phase, this is from cubic, and if you go through several transitions in the crystalline phase to the stable trigonal phase, we see the change of this KFLE from small value, like here, this is less than 1, and then it goes for value which much larger than 1. And so what we see the MIT transition also here. So this is so it's such materials. It shows here insulating behavior, and then it's transformed to the metallic. So here in this system, phase change material system, this also MIT can be understood based on the disorder-induced Anderson metal insulator transition, which change first by decreasing of disorder. So here this is more ordered phase, and then this also driven by a change in charge carrier mobility or scattering at most almost constant charge carrier density. So here these two parameters we have to consider and define. On the next slide. But first, this MIT, it was considered for GST system for germanium antimony, germanium to antimony to tellurium 5, which contains around 20% of vacancies. But germanium telluride, this is another phase in this system, and it does not contain so much vacancies. So if they consider different composition, here germanium telluride contains less than 10% of vacancies on cation sublattice. This is in crystalline phase. GST 1 to 4, it contains around 25% of vacancies, and GST 2 to 5, it contains like 20% of vacancies. And now we can look to different, also to consider this IOFA criterion here. It's written here, and what we can see that there is no change in this parameter, so it stays always larger than 1, and it shows that germanium telluride it's always metallic, so there is no metal insulator transition for this phase, and it confirms again that the metal insulator transition in the GST system, it's driven really by the change of the structural order in the system. Now let us look to some properties of GST material, because it's very important for electrical switching or electrical measurements, and also for device construction. So first of all, electrical conductivity. It also changes with respect to the temperature, so it increases, as you can see here, from the cubic disordered phase to the more ordered trigonal phase. The charge carrier density, however, it stays constant. Here it does not change too much. And the mobility in GST, it's also changing with the increasing of temperature. So the cubic phase, it's low mobile, the carrier is low mobile, and they increase the temperature, so to that stable trigonal phase. And what you should also know that they have vacancies in this system, they lead to tremendous electron scattering, and it results in low mobility and thus insulating behavior. So again, here they have disordered sublattice or disordered vacancies, and here they are more ordered. So now let us look to another interesting application of phase change materials. Before we learned that phase change materials can be applied for optical data storage and for memory, and there is also another application of this material, like for thermoelectricity. You know that thermoelectricity, this is the transformation of thermal energy to the electrical energy, and for that you need materials. There are a huge number of different materials, and tellurium-based or chalcogenized that can be also used. And one application of phase change materials is also for the thermoelectric, as for thermoelectrics. So for what do we need for thermoelectrics? For thermoelectrics, we need like high ZT value. What is it? This is the efficiency. It shows the efficiency of thermoelectric material. It's so-called figure of merit. And ZT, this is equal to EST sigma divided by kappa. So C, this is the Seebeck coefficient. T, this is the absolute temperature. Sigma, this is the electrical conductivity, and kappa is the thermal conductivity. And this is very important parameter for thermoelectric materials. As you see here from this figure of merit, if you can increase this thermal conductivity to a very high large value, then we get a nice ZT. So we can, if we can decrease, if we can decrease this thermal conductivity, then we can get a high ZT value. So how it's for thermal conductivity for the phase change materials? It has been also measured in this publication, and for different compositions. And what we can see that the thermal conductivity change also the structure. So if they start with normal amorphous phase, it has low conductivity, and then it increases to the larger a little bit larger the value. It also depends on the structure, on the composition, on the structure, and also on the presence of vacancies. So the vacancies, they also act as a carrier scattering. So if we consider the composition like germanium antimony, germanium 8 antimony 2 tellurium 11, then we can see that there is no increase in the thermal conductivity. So it seems to be that this phase has not so much vacancies, and so this is one application. Also, there was a measurement on the ZT value for GST and for germanium telluride, and you can see that the ZT value of around 1 and 1.2 can be achieved. It's still low value. We need as high as possible, but it shows you that the material can be applied as thermoelectrics. And so there are also huge research in this direction, how to improve this thermal conductivity, how to increase it, for example, by doping, by mixing, or whatever. So let me conclude this part of my talk. So what we see, what we learned that valence bands of amorphous phase is deeper than those of crystalline phases. Then Fermi in crystalline phases is closer to valence band compared to amorphous phases, and explains the large conductivity in the crystalline states. Fermi of amorphous phase and crystalline phase is closer to valence band, and the material is conductivity is p-type. We also know about the pronounced band tails in amorphous GST. The structural defects along tellurium change in amorphous GST gives a high density of donor acceptor defects pairs, and low mobility tail underlined by Urbach tail due to long pair is signature of mobility H in the valence band. Presence of structural vacancies in crystalline or cubic GST leads to acceptor-like traps, and disorder impacts the so-called metal insulator transition, and this is Anderson type transition, and the effect of structural and composition on thermal conductivity and thermoelectric properties. So this is another application of chalcogenide phase change materials. So now I will proceed with our lecture on local structure and methods of structure analysis. So this is and we have actually two topics. One is local structure and methods of structure analysis, and the second topic is on the chemical bonding in phase change materials. So now let us start with local structure and methods of structure analysis. So just for you, for recap of information. So we already know that the working principle of phase change device, the optical or electrical, is based on the phase change between amorphous and crystalline states. Here, if you apply one pulse set, you can go to the crystalline, and reset pulse with high intensity, you can go back to the amorphous phase. But to understand and to develop better and faster memory, we need to know about the local structure of the both phase. We know some problems with amorphous phase, that it's crystallizes not so fast, so the crystallization time is not fast enough for application, so it could be faster. And the amorphization time, it's good, but it can be better. So, and to improve this properties, for example, crystal set and reset times. We need to know what are the problems here, the amorphous state and the crystalline state. Also, it's important to know the different phases in the crystalline state. So if there are only one cubic phase, like shown here, or there are another phases which can be exist in the system. Because if you know about this, you can think about a new novel application of this phase change materials based on the crystalline materials. So first, let us look to the local structure of the amorphous materials, and then we will look to the local structure of the different phases of crystalline phase change materials. So now I would like to make some definitions. For example, what are amorphous solids? Here we talk about amorphous materials. So, but do you know what are amorphous materials? What is the difference between amorphous and crystalline materials? In one, two.
Amorphous does not have a specific geometry.
Geometry of what?
Like in crystalline, we have structures, right? FCC, BCC, like conventions of crystal structures. They don't have it.
So we talk about long range order. So in amorphous materials we have short range order. In the crystalline materials we have long range order, and this is basically one big differences between these two materials. So amorphous. So more general definition that amorphous solids, these are metastable solids with no range atomic order, and they exhibiting glass transition temperature. So just for general understanding, this is a long range order, this is the crystalline lattice, and here if the long range order is lost, then you have a short range order, and this is the signature of the amorphous solids. So short or medium range order preserved in amorphous solid or glazes, and so they lack of periodic order. So you should have also not only long range order, but it should be also periodic in the space in let's say in the 3D. So they make like 3D structure. And the structure also amorphous structure, it also lacks symmetry and is usually isotropic, same average packing properties in the all direction, and you know that the crystalline solid they are anisotropic, so the properties, physical properties, they change depending on the direction. So now let's go to the description of amorphous materials, so how they can be described. So because if we say it's just amorphous, no, it's a short range order, but it's also have somehow ordering or not ordering. They have own building units, and here what was very nice work on silicon dioxide. This is famous materials, amorphous materials, and in this publication 2021, it was found that for first they prepared one monolayer of this material. It's a glass state. If you can prepare it, you can study the structure. You can see the local structure of the amorphous phase, because it's monolayer. So you see only one layer of atoms. And what they found very nice thing that this SiO2, it consists of rings of SiO and or you see here large rings and small rings and whatever. So and this is one feature of amorphous solid. So they built like a ring, and many amorphous solid they describe by rings and by rings statistics. So you can make here statistics of that, and you can see here what type of ring size you have. The six-fold rings, 4, 5, and whatever. This is the experimental data, and you can also reproduce this data by using, for example, synchrotron, neutron electron diffraction. You can measure the short range order, and then you can make the simulations by DFT or machine learning, and then you can construct like similar structure in the PC. And also you can combine these two data, neutron data and reversor Monte Carlo simulations. This is the normal approach to study the amorphous solids, and then you can also make such ring statistics, build a model with the rings, so to get some insights into the structure. So some definition, what is the ring? In the amorphous solid, a ring is defined as a closed path in the atomic network of classes. Rings can be considered as structural units of amorphous solids. So this is one definition. We will also learn about another definition. And these rings, they are important in the theory of amorphous solids. Now also one method how to study the structure of amorphous solids. This is so-called pair distribution function. And this function, it gives you probability to find another atom at a distance r from the center of atom. So this also based on the diffraction method. And here, if we consider one atom in the center, it gives you distances from this center to another atoms. And so you can study here short, medium range order, but not really chemical order. So it gives you no information on this. And you apply X-rays, electrons, and neutrons to study this short range order by PDF. Also, Monte Carlo simulation can also give you this PDF. You can extract it. If you build your model, you can study by this PDF. So in practical, this PDF, it's calculated from the so-called GR. So GR, that gives you the number of atoms in spherical shell of unit thickness at distance r from a reference atom here, and it's calculated from the structure factor which you measure here at such sources, and then here as Q. This is also important factor, and it's related to the coherent elastic part of the scattered X-ray intensity, and from that you can because this is like a structure factor, I think, yes. So then if you have this GR, you can find this medium range order. Extended X-ray absorption spectroscopy technique. It's also X-ray absorbed X-ray based technique, and it's in this method X-rays absorbed by electrons in atom, and thereby emitting photoelectrons which are internally diffracted by atoms surrounding the absorbing atoms. So this is one of the first technique which was applied to study the amorphous structure of phase change materials. And so in this X-halves, so-called X-halves, we use electrons with energy between 500 electron volt to 500 kiloelectron volt, with wavelength between 2.5 and 0.225 nanometers. At this energy, light is absorbed by matter through the photoelectric effect, and X-ray photon is absorbed by electrons in a tightly bounded quantum core. And so the probability of X-ray absorptions in this case, it gives by Beer's law, and described by these relations. And here I is equal to E0 exponential minus mu t, and I, this is the I0, this is the X-ray intensity incidence on the sample, T, this is the thickness of your sample, and mu, this is the absorption coefficient. And this is the important factor in the XF's spectroscopy in this method, and it's mu. It depends on the material properties. Particularly, it's proportional to the rho z. It's 4 divided by AE3, and so this mu, it's rho. This is the density of your material. A, this is the atomic mass. Z, this is the atomic number, and E, this is the X-ray energy. So what you can see from this absorption coefficient, we can study about, we can distinguish about the types of atoms in the material, and so mu is also dependent on Z and E. And this is the fundamental property of such X-rays. So in the spectra, if you have such XF's Xanis spectra, so what happens here, you have here a jump at particle energy. So it goes like absorption edge. And it occurs at characteristic energy of elements. And this is so-called the fine structure, which can be described by this equation. And then from this data, you can extract mainly the information on distance to the neighbor atoms, type of the neighboring atoms, and number of neighboring atoms. So it's very important methods for study of amorphous materials. Now some experimental data from XFs, for example, on coordination number and nearest neighbor bonds in amorphous materials. So as you can see from here, from this analysis, it's really challenging to analyze some data, and it can be seen in the different data, experimental data. Here, for example, for GST225, they found different distances, bond distances, and coordination number, but they don't found this evidence for tellurium and germanium-antellurium bonding. So, but some found some homopolar germanium and antimon bonds. But 1 year later, it was publication in 2006. In 2007, another group, they found, they stated that there is no evidence on the presence antimony bonds, although they found here these antimony bonds. And also no tellurium bonds, so they confirmed this. And also they found the presence of germanium antimony wrong bonds. And they also support their data by RMS simulation and found the existence of such bonding. Another Monte Carlo simulations, they found also formation of germanium homopolar bonds in amorphous GET, but no formation of germanium or antimony bonds in amorphous GST 225. So analysis of XF's data are not always straightforward. It can be also related to the maybe different techniques of materials preparation. So they can be used. They can be little bit maybe have different, little bit different chemical composition, and so that can bring to different, most probably to different results. Also from XFs, what they found. We found interesting results So this germanium telluride, for example, these distances they belongs to the tetrahedral symmetry positions of germanium and antimony. They found, you see here the difference, that the antimony they are located in the octahedral positions. Why it's so important? It's very important to understand the switching mechanism in amorphous phase change materials, and we will study it, I think, tomorrow on phase change mechanism. So please remember here from XF study, they found that germanium it's located in tetrahedral, and antimony it's mainly in octahedral. And octahedral, this is also the main structural motif of crystalline phase. So how it's related, we will see later. Also, one very important technique to study amorphous materials, but also crystalline materials. This is the Raman spectroscopy. And Raman spectroscopy, it uses a single frequency irradiation or laser beam to irradiate the sample. And the Raman scattering occurs as an elastic scattering process with a transfer of energy between the molecule and scattered photon. And the scattered photon loses energy and its wavelength increases with so-called Stokes-Raman scattering. And the frequency of light absorbs are unique to the molecule or type of bonds, and it allows to figure out type of molecules or atoms, provide both chemical and structural information. But this is a very weak process because only 10 to the 6 or 10 to the 8 photons each scatter is Raman scattered. And there also one disadvantage of this technique. This is laser-based method. You need a laser for Raman method, and if you know that in amorphous phase change materials you can induce crystallization by using laser. So here you should play with different energies of your laser to find the optimum laser energy to study of your amorphous materials. For crystalline materials, it may be not a big deal or issue, but for amorphous materials, you should be careful. So you can induce crystallization of your amorphous materials and then study not really amorphous solid. So, and in Raman scatterings, you identify your substances through so-called characteristic Raman fingerprint. Here, there are some examples for different compositions for GST. For example, for amorphous phase, you see here two typical peaks. This is GST, yes. And then if you crystallize it, you obtain shift of the peaks, and you see the appearance of Raman peaks at different wavelengths. So here, for example, Raman peaks at 1 to 4 centimeter. It's due to the symmetric extraction of A corner sharing tetrahedral units. Again, these tetrahedral units peak B. They are situated at this value and related to vibrations in the antimony units. And for example, from the intensity of these two peaks, you can study something about like doping. In this case, they studied the doping of carbon material. And also position of carbon in which units in this material. So amorphous solids, they can be also studied by using transmission electron microscopy and by specific methods. This is a short introduction to DTM. In DTM, you use thin specimen like on the order of 100 nanometer, and then you illuminate this specimen by electron beam, by focused or parallel beam, and then you have several scattering underneath of the specimen, and you can collect these scattered electrons and then study about your material. Here, in the case of TM, you can study the structure, local structure, and chemical composition in one method, but in one setup. But there are different methods, experimental methods, how to study the structure of amorphous solid. For example, fluctuation electron microscopy. This is one of the method, and here you can study about the also short range order in the material, but it gives you not really the distances in this case. It gives you the like clusters or domains on which length scale this ordering is occurred. So this is some experimental data shown existence of short range order on the scale of 1 to 2 nanometer. It was so this samples, 3 samples from different group as deposited. They were studied at one setup, and they showed the existence of 1 to 2 nanometer scale. But in our group, in our publication, they found structural order on 3-4 nanometer scale. So different one method, but two different results. But one also thing what you should carry in the TM, that you use electron beam, and electron beam can crystallize your material. I will show you also some examples on structural changes using electron beam. So if you use wrong setups, you can also increase the order in your material. And you can influence the structure. But overall, there is a medium range order in the amorphous GST existing on the scale like between 1 and 4 nanometers. Also, you can study the amorphous materials by using RDF, as I introduced you before. In the TM, what you collect nanobeam electron diffraction, and then you can calculate the reduced density function. Here in the TM, you can use the size, the beam size, so it's very small, like a 2 nanometer. You can go down as 2 nanometer. And what we did here, we studied the S-deposited and melt-quenched material. It was melt-quenched by laser, and we were interested in the bond, in the length, in the distances in this amorphous materials. And from RDF, what we found like the pronounced peak at 2.8, and this shows the defective octahedral sites of germanium antimony in the amorphous material, but we did not observe this 2.61 distance, which belongs to the tetrahedral sites, which was found by XFs. This may be due to because in XFs they found that only 35% of germanium, overall germanium, they can be seen at these tetrahedral sites. So maybe it was not sensitive. So the volume which are illuminated here, it was let's say thickness of the sample 50 nanometers. So maybe we did not the signal from tetrahedral sites maybe was too low. But in another publication here, like using angstrom beam electron diffraction, and they used really angstrom size beam, very small, and they combined it with Monte Carlo simulations. So this is the experimental electron diffraction pattern, and there's a simulated pattern from this structure. And they also confirmed that the structural motif of amorphous material is distorted octahedron. So here they used beam size even smaller than in our work. It's 0.8. This is 2 nanometer, but the results the same. So the same conclusion. So the main structural motif is this octahedron. But again, just think that we use here very small volume in the TM, and XF's the size is or volume, studied volume is much larger. Maybe this is the difference can be due to this. Now the amorphous materials, they can, as I said, they can be also studied by using atomic simulations. So you can first make your model and then look to the simulations, to the results. And here, and for particularly to the ring statistics, what is important in amorphous materials, as I said, this is the ring statistics. And after model construction and letting to simulate it, to quench it, for antimony, amorphous antimony telluride, in this publication, the authors found different rings with different lengths, but the fourfold rings, they dominated in amorphous antimony telluride. So they found also that existence of fourfold ABAB rings with 81%, and total volume of voids they found 20%. So the ring structure of amorphous germanium telluride and amorphous GST225, they also, you can see, they also have fourfold, 5, 6 different rings. So broad distribution size of the rings, but with large fraction of 4, 5, and 6-fold rings. The amorphous germanium telluride and GST, they also have pronounced maximal fourfold ABAB rings, 86%, and 1/3 of germanium are tetrahedrally bonded in 34% in amorphous GST and 30 in amorphous germanium telluride. So XFs and the theoretical simulations, they somehow in line, they confirm the existence of this tetrahedrally bonded germanium, but TM does not confirm this. So because of some issues, as I talked before. AST, this is another phase change material, silver indium antimony telluride. It has even larger ring statistic distribution. The most 5-fold rings here, they have the large number of 5 rings, but also a huge difference of another rings. And here they don't have A, B, and B rings. They are not so significant in this material. So now let's look to the medium range order in amorphous GST225. This is the structural properties of S deposited and mel quenched GST from theory and experiment. So there are some reports that the amorphous S deposited and mel quenched structure of amorphous GST, they have different structures. Also, if you operate your devices at the optical or electrical, first you make several switching. So you make first deposition and then let the device several times to switch. And at the end, you switch between melt quenched and crystalline state, not between S deposited and crystalline. So you have always melt quenched crystalline phase transition. And so there are some results for S deposited and AD. This is S deposited. This is mel quenched. And here we see some little bit different environmental for germanium. For example, here that this is predominantly tetrahedral and S deposited, also from experiment, and this is defective octahedral in mel quenched. Then the fraction of tetrahedrali coordinated germanium is significantly larger in amorphous, in S deposited state than in mel quenched, so it reduced. And main coordination of germanium is 4 and antimony is 3, and this is lower than ideal octahedral value of 6. So this is from the experiment, and the ring structure of amorphous GST from density functional theory we looked before, but saw some recap, so that the crucial structural motif, this is 4 and 6 AB and B rings with alternating atoms of A and B type. So A here, this is the germanium antimony, and B, this is tellurium. And also the simulations shows the existence of some cavities in the amorphous structure, like up to 12%. So from this we can see difference between mel quenched and S deposited phase, mainly in the local environmental of germanium. So this is tetrahedral in S deposited and defective octahedral in mel quenched. So now, if you talk about phase change materials, we want also to look to the local structure of another amorphous solids, and here I would like to compare the ring statistics from DFT, calculated from DFT for SiO2 glass, magnesium SiO3, magnesium 2 SiO4. This is spinel, and here this is the data, and we want to compare it with the ring statistic of typical amorphous GST225 and amorphous germanium telluride. So what we can see in the case of glasses, that the ring statistics, it's dominated mainly by 4, 5, 6, 7, and 8 rings. Here they have the rings between 4, 5, and 6 fold, and for spinel, this is a little bit narrow distribution of rings, 2, 3, and 5. For monolayer SiO2, as you can see, also the distribution is 5, 6, 7, which is very nice in agreement with the DFT calculations. So this is between 4 and 8, here 5 and 7. And in the amorphous GST and amorphous germanium telluride, they have this structural motif, these rings for amorphous GST. This is 4 and 6 fold, mainly 4 and 6 fold, and 4, 6, and 8 AB rings for GST225 and germanium in germanium. So overall of the rings, these are also broad distribution as in other glasses, but here the interesting, these are these AB rings, and the distribution here 4, 6, and 4, 6, and 8. So now let me switch to the crystalline phase change materials, but I think so. I think we can make so we can stop here for a break and for a question round. So if you have some questions, please ask me. And then after the break, we can continue our lecture. Yes, please.
Professor, you were just talking
So sorry, you need microphone.
So you were just talking about Monte Carlo simulation,
Mhm.
RMC simulation. So how do we decide the sample size here, like for proper distribution and things? How are we going to decide on what factors?
Yeah, we need also to support this by experimental data. First, to extract the distances from the X-ray data, and then you put into the Monte Carlo simulations, and then it gives you a structure.
So is there any standard that we should take this many samples for better, uh, you know, uh, like performance, or like, is there any rule of thumb that we should take this many samples?
No, there is no rules. You need to first make experimental data. You should measure it.
Okay.
You should know the distances
Okay.
in your experimental setup, and
Mhm.
then you put it to the Monte Carlo simulations, and then the simulations gives you a structure,
All right.
and then you calculate again RDF.
Mhm.
Then you adjust your structure, and you look. This is like iterative to find to fit the experimental and simulated data.
Okay. Okay.
And you have a nice fit. You can say, yeah, it could be my structure, but
Okay.
you can think you can create different structures
Okay.
which can fit this RDF.
So we are gonna run a lot of iterations.
Yes,
Okay.
yes. Yeah.
All right. Thank you. So another follow-up question is, you were talking about something on foil 24 in the other foil. Like, I wanted to understand, does lattice-induced phonon scattering has an impact on the thermal conductivity of uh, these structures that you're discussing?
Yes, it has. Yeah.
Okay, and how are we going to take care of?
Again, the question how the
Yeah, so lattice-induced phonon scattering on the thermal conductivity. Can you shed some light on it, like
yes,
on the material?
So if you have the scattering on the defects, you reduce your thermal conductivity. This is the main point. So to reduce it, to make materials with reduced thermal conductivity, you need to create like materials with many interfaces, grain boundaries, and make dopings or something like that.
Okay,
This
okay.
is
All right. Thank you.
Sir, regarding the TEM, like for our study, usually we used to hit it on some hot plate, and then we hit it for some 45 minutes or something like that.
Mhm.
And then I find it from the images from for the HR TEM. So some amorphous and some crystalline natures are seen. Like both the phases are visible in that, I think. So can you share some light on like
At what temperature did you?
like I hit it to above the crystallization temperature around 300 degrees Celsius. Crystallization is around one.
And what was the composition?
Composition is GET and some arsenic dope.
Yeah, okay. If you dope with arsenic, it's the crystallization temperature is very high,
Okay.
and so you need to increase your temperature
Okay.
or increase the crystallization time. We did some crystallization experiment with selenium. It has also high crystallization temperature. Even at 200 centigrade, it's still amorphous, but after 300 centigrade, it's crystalline. So I think it's normal that you have amorphous and crystalline phase.
Okay.
So the doping it increase the use or selenium or arsenic. This is more. This is another type of chalcogenide. They have a larger crystallization temperature.
Okay. And so regarding the DFT for DFT measurement, kind of, if we want to draw, like I'm actually new to like exploring DFT currently, but if you want to draw the crystal structure of some material for GET or something like that, then how to go about, like first usually I use this Gaussian line or something like that. Then we used to throw with Gauss View software. So
Okay, I'm not really expert in this
okay.
DFT calculation, so
Okay,
I can bring you maybe basics, but not this details how to make it. So
okay.
sorry.
Thanks.
Hello, sir. So one question regarding Raman scattering. So as we seen from amorphous to crystalline transformation, peaks are absence. Means we have seen peaks are absence from the transformation from amorphous to crystalline state, or FWHM of the peak decreases or increases. So actually, what happened inside the while transformation actually
Sorry, excuse me again.
in Raman studies, while we go for amorphous to crystalline,
Mhm.
so there is a some peaks are absence, no? Suppose we have seen some peaks in amorphous state, but we can't see some these peaks in crystalline too.
Okay.
Okay.
But
Means my question is that actually what happens inside
yeah, but it's I think it's temperature and compositional dependent.
okay.
So I think my idea was to study it's the different temperatures to see if the peaks are disappearing.
Okay.
I think maybe it was not a full crystallization. So if you still have a presence of some peaks from amorphous phase, it's a signature of that you have both phases in your material.
Thank you, sir.
Yes, please.
Yeah, so
So in the beginning of this session, I think in foil 1 or 2, you were discussing about resistivity versus temperature, where we saw like non-metal and metal.
Mhm.
There was an equation where we say that differentiation of like d rho by dt is less than 0, so that's a non-metal, and if it is greater than 0, so it's a metal. So I actually did not catch like the GST 225. Does it show both metallic and non-metallic behavior based on that?
It shows metallic and non-metallic behavior. Yes, the amorphous and cubic phase, this is non-metals, and this stable phase, trigonal phase, it shows metallic behavior.
Okay, so it shows dual behavior.
Only the germanium telluride.
Okay.
It does not show because it contains very less number of vacancies.
Okay.
Sometimes some reports 10%, some says no vacancies. So there is, and this is the effect of vacancies on this metal insulator transition, or non-metallic metallic.
Okay.
It's nice to say insulator, but non-metallic can be insulator
Mhm.
and not. Yeah, it's yeah.
Okay. Yeah. So follow-up question on this. You were talking that GST has a 20% vacancy in
Yes.
some foil. I forgot. So and we also talked and we also saw that no low mobility and things will affect it. So how low mobility will have the insulating behavior? I didn't catch that part actually.
Yeah, I think this is the experimental data. And yeah, this is experimental data. And you see here the mobility mu and then these values. And here the non-metal, it shows very low mobility.
Okay.
It's less than 1. And here it goes more than 10 for metallic.
Okay.
So it has higher mobility, but the same number of the charge carriers. So this is only the mobility that changes, and that brings to the metallic behavior.
Okay.
Actually, the both phases, they're semiconductors, non-degenerated semiconductors, especially with this phase. But the metallic behavior is really because of higher mobility of carriers,
Right.
compared to non-metallic phase like insulator phase. Yeah.
All right. Yeah. Thank you.
So if no more questions, then we can have a short break, 5 to 10 minutes. So probably we have a tea outside. Tea is there. Okay, so just have a tea and then quickly come back. Then we'll start after a short break. Thank you.